For more than a century, the Panama Canal has been one of the most important shortcuts on Earth. It slices through the jungle connecting the Atlantic to the Pacific. Before it existed, ships had to sail around the southern tip of South America, an extra 8,000 miles of ocean. The canal changed global trade forever, but over time something changed again. Ships grew, container vessels doubled in size, oil tankers expanded, global trade intensified. The original locks built in 1914 were no longer big enough. A new class of ships emerged. They were called post-Panamax. Too wide, too long, too heavy for the old canal. If nothing changed, these ships would bypass Panama entirely. Trade routes would shift, ports would adapt, and the canal would slowly lose relevance. So Panama made a decision. It would not replace the canal. It would upgrade it, not with minor repairs, but with a $5 billion expansion project deep inside the jungle. The goal was radical. Build a new set of locks large enough to lift and lower the biggest ships in the world. Not with pumps, but with gravity. A water elevator capable of moving vessels weighing more than 100,000 tons. And it had to work beside the original canal without shutting it down. This was not renovation, it was reinvention. Because if the canal could not grow, global shipping would simply outgrow it. And in the middle of tropical heat, thick jungle and constant rain, engineers began building one of the largest hydraulic systems ever attempted. Building a new canal inside a working canal is already complex. Building it in a jungle makes it extreme. Panama's heat is relentless. Humidity hovers near saturation. Rain can flood a site in minutes. Steel rusts quickly. Concrete cures differently. Yet this is where the new locks began to rise. Each lock chamber is the size of several football fields. The walls are massive. Behind their smooth surfaces is a dense forest of steel. Thousands of tons of rebar are tied together by hand, forming a rigid skeleton inside the concrete. This steel cage is not decorative. It absorbs pressure from millions of gallons of water and the weight of the ships themselves. Once reinforcement is in place, concrete is poured in carefully controlled sequences. You cannot pour it all at once. Heat from hydration can crack the structure. So engineers layer the pours, section by section, meter by meter. Vibrators are inserted to remove trapped air. Alignment is constantly checked. Even small deviations can multiply across walls that are dozens of meters tall. The scale is overwhelming. Cranes swing overhead, trucks deliver aggregate. Workers operate in shifts to avoid peak heat. All of this for a structure that will never move, because once the lock walls cure, they must resist decades of hydraulic force without shifting even a few millimeters. And these are not simple walls. They are chambers, designed to hold and release massive volumes of water with precision, to turn elevation into motion, to lift ships through nothing but gravity. But concrete alone does not make a lock. The most critical element is something far more dramatic: the gates. And they are unlike anything built in the original canal. If the lock walls are the skeleton, the gates are the muscle. Each gate in the new canal stands nearly 30 meters tall and stretches 50 meters wide. They look solid, but they are not. Inside, they are hollow steel boxes, designed to float. This was deliberate. Traditional gates rely entirely on hinges to support their weight. At this scale, that would be impossible. So engineers reduce the load by letting water carry most of it. When closed, each gate displaces enough water to lighten itself. It still weighs thousands of tons, but it behaves differently. Instead of swinging open, these gates slide sideways into recessed chambers, like massive steel drawers. This reduces mechanical stress and allows precise control over movement. Precision matters. The gap between gate edges must stay within strict tolerances, at times less than 100 millimeters. Too tight and friction increases. Too loose and water leaks uncontrollably. Alignment checks happen constantly. Laser systems confirm position. Hydraulic rollers guide motion. Engineers monitor torque sensors as gates settle into place. Even temperature matters. Steel expands in tropical heat. Clearances must account for thermal movement throughout the day. During installation, each gate was lowered slowly into its chamber, millimeter by millimeter. Watch the guides. Check the alignment. Adjust the rollers. Once sealed, the gates must withstand millions of gallons of water pressing against them. And they must open again smoothly thousands of times. Because without the gates, there is no lift, only uncontrolled flow. But even with perfect gates lifting ships, this large would normally waste enormous amounts of water. The original canal empties fresh water into the ocean with every transit. The new system had to do something smarter. It had to recycle gravity itself. Every time a ship moves through the original Panama Canal, millions of gallons of fresh water are released into the sea. That water comes from Gatun Lake, a reservoir fed by rain. For a century, this system worked. But bigger ships mean bigger lock chambers, and bigger chambers mean more water per transit. Without change, the expansion would have drained the lake faster than it could refill. So engineers redesigned the entire hydraulic system. Instead of letting water escape, they built 3 water-saving basins beside each lock chamber. These basins are enormous. Each one is positioned at a different elevation. When a ship is lowered, water does not flow directly to the ocean. It flows sideways into the basins. Gravity does the work. No pumps, no external energy, just controlled sequencing. Valves open in stages. Water levels equalize between chamber and basin, then between basins. By the end of the cycle, about 60% of the water used in a transit is captured and reused. When the next ship needs to rise, that stored water flows back into the chamber, again by gravity. The choreography is precise. Open too fast and turbulence increases. Open too slow and delays compound. Engineers modeled every flow rate, every pressure change. Sensors monitor levels in real time. If a valve misbehaves, the system corrects immediately. This innovation transformed the expansion from a simple enlargement into a smarter canal, one that handles larger ships while protecting its water source. Without these basins, the new locks would not be sustainable. But designing the system on paper was only the beginning. Before the world could trust it, the canal had to prove that it worked. With real ships, under real pressure. Before the world saw celebration, there were trials. The first ship to enter the new locks was not carrying cargo. It carried pressure. A chartered vessel brought in for one purpose: testing. Tugboats guided it slowly into the lower chamber. Unlike the original canal, there were no electric locomotives pulling it along the walls. The new system relied on powerful tugboats to maintain position. Clearances were tight. The ship looked enormous inside the chamber. From the control room, engineers watched live data. Strain gauges embedded in the walls measured structural response. Flow meters tracked water intake rates. Torque sensors monitored the movement of the gates. As valves opened, Water rushed into the chamber. The ship began to rise, slowly, silently, gravity doing the work. Then came the tension. One sensor spiked. A secondary torque reading rose faster than projected. Engineers paused the sequence. Flow rates were adjusted. Intake slowed. The system stabilized. This was the purpose of testing, not to prove perfection, but to find weaknesses. The ship completed its transit. Lower chamber, middle chamber, upper chamber. Each cycle measured, each response analyzed. By the end of the day, the new locks had performed exactly as designed. But testing did not stop there. Simulations ran repeatedly. Extreme loads, emergency scenarios, unexpected valve behavior. Because if a failure occurred, it would not be small. A misaligned gate, an uncontrolled surge, the integrity of the entire system would be at risk, and global shipping would feel it immediately. So engineers kept pushing the system until confidence replaced doubt. Only then could the canal prepare for its first true moment, when the world would be watching. Testing a lock system is one thing. Operating it with real-world uncertainty is another. The new Panama Canal locks were not just larger. They were more complex, more sensors, more valves, more moving mass. That means more variables. During advanced trials, engineers deliberately stressed the system. They increased flow rates. They tested emergency stops. They simulated power loss mid-sequence. What happens if a gate stalls halfway closed? What if wind pushes a vessel off center? What if a valve opens too quickly and creates unexpected turbulence? Every answer had to be discovered before commercial traffic began. Strain gauges were closely monitored. If wall deflection exceeded projections, adjustments were made. Hydraulic pistons controlling the gates were tested under uneven loads. Torque spikes were analyzed. In some scenarios, engineers halted operations and recalibrated control algorithms, not because something had failed, but because something might. The system had to anticipate risk before risk appeared. Heat added another complication. Tropical temperatures change material behavior. Steel expands. Hydraulic fluids respond differently. Clearances shift. So calibration happened throughout the day. Morning tolerances were not identical to afternoon tolerances. Wind also became a factor. Large container ships act like sails. Gusts can push them off alignment. If a ship strikes a lock wall, damage could cascade. So wind thresholds were established. Above certain limits, transits paused. Better delay than disaster. By the end of this phase, the canal was no longer a construction site. It was a monitored machine. One designed not only to function, but to detect its own weaknesses. Only after this could the project reach its most visible moment, the inauguration, when the world's largest ships would enter for the first time under global attention. After years of construction, months of testing, and countless adjustments, the moment finally arrived. The container ship Costco Shipping Panama waited offshore. It was chosen for a reason. Large enough to represent the future, small enough to fit safely within the new design limits. As it approached the Atlantic entrance, tugboats took control. Wind speed was checked. Water levels confirmed. Gate positions verified. Inside the control room, every screen was active. This was not just ceremony. It was proof. The ship entered the lower chamber slowly. From above, the scale became undeniable. The lock walls towered over the vessel. The gap between hull and concrete was precise, but controlled. Valves opened. Water surged into the chamber. The ship began to rise. Cameras broadcast the lift to the world. But inside the system, sensors were still working. Strain gauges, pressure monitors, torque sensors, everything reading within limits. As the gates opened and the vessel advanced to the next chamber, the expansion stopped being theory. It became reality. When the ship cleared the final gate and entered the Pacific, cheers erupted. But for engineers, the relief was quieter. The system had performed under global scrutiny, and it had done so exactly as designed. Yet even that day was not the final test, because the future of the canal would not be defined by container ships alone. It would be defined by something larger and more demanding. Just days after the inauguration, a different kind of vessel arrived. An LNG tanker. Longer, heavier, more sensitive to movement. These ships could never pass through the original canal. Their width exceeded the old limits. Their value made risk unacceptable. But now the expanded locks stood ready. Guided by tugboats, the tanker entered the chamber. Wind conditions were checked again. Clearances confirmed. The scale felt different. The walls seemed closer, the margin tighter. But the system held. Water flowed from the basins. The chamber rose. Steel gates sealed perfectly behind it. This was more than another transit. It marked entry into a new shipping market. LNG exports from the United States could now reach Asia through Panama without detouring around South America. Transit times shortened. Fuel costs dropped. Trade routes shifted. Ports on both coasts adjusted their infrastructure to receive larger vessels. The expansion did not just enlarge the canal, it reshaped global logistics. Today, the new locks operate daily. Container ships, bulk carriers, energy tankers, each lifted by gravity through a rainforest corridor that once seemed fixed in time. The Panama Canal did not compete by building faster. It competed by building smarter. A hydraulic system hidden in the jungle designed to handle the weight of global trade. And in doing so, it ensured that a century-old shortcut would remain at the center of the world's oceans for decades to come.